Sample problem 8.9. Formaldehyde, CH2O, which can be used to preserve biological specimens, is commonly sold as 37% aqueous solution, meaning it's dissolved in water. Use formal charges to determine which skeletal arrangement of atoms shown here is the best choice for the Lewis structure of CH2O. So we have two arrangement of atoms, and we're asked to use formal charges to figure out which one's best, okay? Remember, formal charges closer to 0 are better. This is a neutral molecule, so all the formal charges should add up to 0. So they've done much of the work for us already. We just need to finish it up for them and then do formal charge. So let's count the number of valence electrons we would expect. Carbon is in group 4A, so that's 4. Hydrogen is in group 1A, so that's 1. And oxygen is in group 6A, so that's 6. There's 2 hydrogens, so that gives us 12 electrons. In each structure, we've already used 6. There are 3 bonds, so that leaves us with 6 electrons. So here we go. We got 6 electrons to distribute. So what I'm going to do is I'm going to put 2 here, another 2 there, so there's 4, and then 6 I've run out, right? We're not going to put any on the hydrogen because hydrogen maxes at 2. We could have put 4 on the oxygen and 2 on the carbon. That would be fine as well. For this one, let's put 2 here and then 4 there. Actually, you know what? Coming back to what I said in an earlier lecture, and certainly that's fine. We could have done it just the way I showed you right there. But I'm going to go ahead and do it just like I said in an earlier lecture. I'm going to get the surrounding atom up to 8, and then we'll go from there. Okay? So the issue here is on the left one. We'll take this structure over here. The carbon on the left has 8 electrons, but the oxygen only has 6. So we're going to take a pair, push it over here to share that pair of electrons. We'll use the double arrow to represent pushing a pair of electrons. Now we have a double bond. Now it looks like each atom in the center, meaning the carbon and the oxygen, each have 8 electrons. Fine, each one has 8, we're good. Now the one on the right, the carbon only has 6, but the oxygen has 8, so same thing. Let's push a pair over, form a second bond, a double bond, we call that, right? Now we have a double bond between the carbon and the oxygen, and a single bond to each hydrogen. There we go. Now, we've got the octet rule set for each, but which one's right? Which one's most likely the structure? Well, it turns out it's the one on the right, and the way that we'll tell is by doing formal charge calculations. So I'm going to do the carbon over here first. So it would be carbon is in group 4A, so it has 4 valence electrons. The number of associated electrons would be 2 for the lone pair, and it has 3 bonds. So that's 2 minus 5, I'm sorry, 4 minus 5, minus 1. So the carbon here is at minus 1. What about the oxygen? Group 6A, so 6 valence electrons, minus 1 lone pair, so that's 2 and 3 bonds. So that's plus 1. So this has a plus 1. Now you remember what we said earlier was that if you're going to have positive or negative formal charges, non-zero values, the more electronegative atoms should be negative. Well, this is the reverse of that. Oxygen has an electronegativity of 3.5. Carbon's only 2.5. So we have it reversed. This one has the negative. This one has the positive. That's not good. But let's check out our other structure over here. I'm going to do carbon first. 4 valence electrons minus 0 lone pairs, but 4 bonds. See how we get a 0 there? And now let's do the oxygen. Group 6A minus 4 non-bonding electrons, 2 lone pairs, that's 4, plus 2 bonds. That's 0. So this is 0. So this is clearly the better choice. This is the better choice because not only does it not have a positive formal charge on the more electronegative atom and a negative formal charge on the less electronegative atom, it actually has 0 values for the formal charges altogether. So 0 formal charges would be better. The formal charges add up to 0. That's the structure we want. So this would be our answer. Both fulfilled the octet rule, but the formal charge told us which structure was better.